Hello, everyone. Welcome to another UAA Professional Development Seminar Series. Our guest speaker today is Dr. Felicia Cicilio. Dr. Cicilio is a research assistant professor at the Alaska Center for Energy and Power, ASAP, at the University of Alaska Fairbanks. Dr. Cicilio earned her PhD in electrical engineering from Oregon State University in 2020, where she worked with power transmission operators and reliability coordinators in the United States, a mini-grid company in Lesotho, South Africa, and Idaho National Laboratory. Thank you very much for accepting our invite, Dr. Cicilio, and giving us a talk today. The stage is yours.
Let's see if I can get this right on the first try.
Beautiful, looks good.
All right, one more moment. Adjusting on my end. All right, well, thank you very much. My name is Felicia Cicilio, and I'm a research assistant professor at the University of Alaska Fairbanks, and I specialize in power system modeling and dynamics. Today, I'm going to be talking about power systems engineering. We'll start at a high level, discuss how electrical grids are changing, identify some terminology and what I mean by dynamic power system modeling, and then do a deep dive into defining our problem space in relevance to power systems. So now I want to take a look at this picture. I really like this picture. I think it demonstrates well the incredible size of electrical grids. Excluding communication networks, electrical grids are the largest man-made machine. They're incredibly complex and interconnected, or not interconnected, depending on where you are in Alaska or the world, but mostly interconnected. Power engineers design, plan, and run these electrical grids. And at the end of the presentation, I'll discuss some of the types of jobs in the industry and hopefully convince you that these are some fantastic jobs. So how is the electrical grid changing? Depending on where you are in the world, the electrical grid is undergoing some rapid transitions, at least in comparison to previous decades. We'll go into detail on these topics, including inertia, location, meaning going from centralized to decentralized, and dispatchable versus variable. There are other ways electric grids are changing, such as increases in digitalization, which is talking about home smart meters and phasor measurement units, but I won't go into these topics today. Historically, we have generated the majority of our electricity from large synchronous generators fueled by fossil fuel combustion or the potential energy from hydro generators and also nuclear. These figures show the source of electric energy that is consumed in the United States from 1949 to 2019. I know the text is small to read, so I'll point out the key data. On the top, we have more traditional energy sources like coal, hydro, and nuclear. You can see nearly all of these have leveled out, if not decreased in recent years on the right-hand side, except for natural gas, which we'll discuss later. These types of generators have large rotating masses, which carry a lot of inertia. So when there are disturbances in the system, like a generator trips offline, the large amount of inertia prevents the system from responding rapidly, which produces a delay that allows other control systems to kick online to prevent system collapse. It's like if you're driving a large truck 65 miles per hour on the highway and you take your foot off the gas, you'll still keep moving forward for a while, even if there's a bit of an uphill. Now, solar and wind, seen on the bottom plot, do not have rotating machines that directly physically connect to the grid like large synchronous generations. They don't have inertia. Now, I say that with the caveat that they can use controls to have inertia-like responses if paired with storage, or the generator has to operate at lower than the maximum power output. But the key takeaway is that they don't have rotating machines that create this inertia. So existing control systems that act to stabilize the system after faults are designed to work with synchronous generators that act on this longer timescale than inertialess solar wind. Therefore, as your system adds more and more solar, wind, and/or storage, there has to be an adjustment to control and protection systems to account for their different, faster dynamic behavior. Next, we'll talk about generation placement. These are two models of a power system shown as a single line diagram. On the left is a distribution system. These are the lower voltage systems that bring electricity directly to houses and buildings from substations. The system on the right is a transmission system, which is used to take electricity from large generators to the substations. Historically, generation really was only on the transmission grid, and the properties of transmission grids are different than distribution grids. And you can see it here. The transmission system is more meshed and interconnected, and the distribution system is radial. Each line goes to a dead end. The radial systems were designed assuming there was no generation in the distribution system, meaning no two-way power flow. With rooftop solar and storage, and with small wind generators that people put at their houses, there's now distributed energy resources, which I'll call DERs. This means there can be two-way power flow, and there are generators that are, and these are generators that are not on or controlled by the transmission system, which brings me to my next point of, well, now you can see approximately where those generators are. This will bring me to my next point of dispatchability. Dispatchability is the ability to provide power when called upon by utility. It's typically done at the transmission level, as previously mentioned, or it can also be dispatched from internal control systems, which we'll touch on later. It is well understood that solar and wind are variable. Their energy source isn't around all the time, and because of that, they aren't really dispatchable. So you can't say turn on or turn off right now. What you see happen is something like on the right. That is the famous Californian duck curve. It shows from 2012 to 2020, the load as seen from the transmission system decreased to the lowest point in the middle of the day. And that is from solar, specifically rooftop solar. It shows up here as a reduction of load because it's on the distribution system. From the perspective of the transmission system, the load is measured at the substation upstream of everyone's houses. Therefore, the rooftop solar generation is lumped all together with the load demand. First and foremost, I want to say that this massive integration of rooftop solar is a huge success from an environmental and engineering perspective. It also presents new challenges, like that increased ramp you can see in the figure. When the sun goes down, rooftop solar is no longer offsetting that load demand, so you have an incredible ramp to the largest load demand of the day. This means that upwards of 14 gigawatts needs to be put online in a matter of a couple hours. Now, I want to pause here for a moment to say that all these changes and challenges that are caused that I've been discussing are not unsolvable, and many already have solutions. We just need to implement them. This is an incredibly exciting time to be a power systems engineer, as there are new engineering, policy, and practical challenges to solve, and new controls and technologies are being developed to meet these challenges. So next I want to shift to how do we classify these challenges, and then how do we solve them? To attack this, we have power system stability classifications and specific models that are used to simulate them. Now let's talk about events. These are the types of events that happen in electrical grids and the approximate time scale that they occur on. So we talked about variability previously and the load ramp that caused in California. That type of event happened over a couple of hours. The wind can vary as fast as a couple of seconds. So you can see in the diagram that variable energy resource deviation ranges from around a second up to an hour. On the far right are capacity markets and planning activities. These are engineering practices and market structures whose implications are very long-term, on the order of years. Then there are daily energy markets, where generators are planned to be dispatched the next day, or in some places, they have markets that operate every 15 minutes, such as the energy imbalance market in the Western Interconnect. Then moving left, we start to get into events. They're getting to what I call dynamics. Demand response is a control that signals specific loads to turn on or off as a regulation mechanism. Then there is frequency regulation, which is also enacted by power sharing controllers, usually directly connected to the generators. Then there is inertial response, which was discussed earlier about inertia, and then protective relay operations. Now, protective relays are what are used to disconnect devices to either protect themselves or prevent cascading outages. Not shown in this figure though, but located around where protection relay operations is also fast inverter controls. Inverters are what are used to convert DC power from solar, wind, and batteries to AC power that is synchronized with the grid. From a simulation and modeling point of view, there is a large difference in how you simulate these events, whether you are in steady state or not meaning dynamics. And for power systems, from a simulation point of view, this happens around a second. So how are we defining steady state versus dynamic simulation or modeling? If you are in steady state, you use one type of method to solve the system of equations of the power system, which is power flow analysis, which is what can be used for energy balance types of problems and dispatch. If you are looking at dynamics, additional models are needed, typically modeled using differential algebraic equations, which are used to model the dynamic components, such as generators and dynamic loads, like power electronic loads, and motor loads, like large fans. And there are various levels of these more detailed models. Here I'm showing the difference between what I mean by steady state and dynamic. So if you were to do steady state analysis of a power system at two different snapshots of time, say before and after a large load was turned on, what your steady state solver would tell you as an answer is the value in the A block and the value in the B block. Oh no, there we go. However, this won't capture the dynamics that occur when transitioning to state A to state B. In between these snapshots, the dynamic response of the system could exceed stability limits, such as power line loading limits or voltage magnitude limits. So if you think there might be concerns for dynamics, or you know there's phenomena in the system that could cause dynamics like this, you would need to do dynamic simulation and go beyond just steady state simulation. Oh no. I'm sorry, can you hear that? Can anyone else hear the recording that was playing on that slide? I'm sorry to interrupt this presentation.
Oh, no, I don't think I could.
Okay, excellent. I'm going to just, okay, no one else can hear that, good. So now let's go back to the events and look at the dynamic events. Here are some of the missing shorter time step events from the previous diagram. These would all be classified as dynamic events. Some of these are relevant to only synchronous generation, some to inverter-based generation being solar, wind, and batteries, and some to both. Rotor dynamics and inertia response are specific to synchronous generation. And you'll notice that inverter controls and stability dynamics occur much faster than the other dynamics, with the exclusion of lightning propagation. However, lightning propagation is a specific phenomenon that is not a very typical event simulated in system level studies. So you can see the inclusion of inverter-based generation is driving the need for faster timescale simulation of events to be able to control and maintain the stability of the system. When a system has only a few inverter-based resources, that may not have a large contribution, and the faster timescale issues might not be of concern. But as more inverter-based generation is added, these assumptions might need to be changed. Now, going from events and stability to how do we simulate these events to design controls or implement devices to mitigate new stability concerns. For power systems, steady state analysis is performed with power flow analysis, as mentioned, and dynamic analysis is performed with electromechanical and electromagnetic simulators. These are different types of simulators that make different types of assumptions, and you can kind of see some brief summaries of those assumptions in the blue bubbles. Electromechanical simulators that use positive sequence, that is that they transform the three phases into sequence components, are called positive sequence simulators. And those only produce accurate results when it can be assumed that the system is balanced, meaning that all three phases, A, B, and C, are carrying approximately the same amount and type of power. Now, electromagnetic simulators do not assume phase balance and are able to capture harmonics associated with the high frequency switching elements of the inverters. Now, the detailed models of these devices, here we'll talk about inverter-based resource models specifically, also correspond to this timescale and these different simulators. Here is a generic diagram of an inverter-based resource model that would be used in electromagnetic simulation. You have the actual generator up top that is producing the direct current power directly or through another converter, such as with wind. Then you have switching devices that convert DC to AC. Then there are nested control loops. These control loops increase in time step, where the innermost control loops control those voltage and current waveforms. Then there's a power sharing control, such as droop, and then frequency and voltage restoration loops that are associated with voltage and frequency stability. Additionally, there is the protection trip functions seen in the voltage and frequency ride-through block, which either trips or leaves the generator on during voltage or frequency swings. These are like from disturbances such as generators or loads tripping on or offline, large generators loads tripping offline, or faults happening in the system. When the level of detail, as shown in this model, goes down to the switching level device, these models are very computationally demanding to simulate and are actually often only used to calculate switching losses of the inverter or simulate different switching modulation techniques, or they use switching models to validate lower resolution or lower detail levels of models. And this is what would be used in an electromagnetic simulator. So next, moving towards a slightly simpler model of an inverter-based resource, this would be a type of average model. Here, the switches are replaced with current and voltage sources, and the modulation, the pulse width modulation that was in the earlier diagram, is not included. These types of models can still model all the power sharing and voltage and frequency stability controls, and they are less computationally demanding. However, they are implemented in electromagnetic simulators, and in an electromagnetic simulator, less computationally demanding is still very demanding. These types of models are typically only used to model one or two inverters together and are not modeled in conjunction with the rest of a power system, such as if you were trying to model and simulate an entire region or utility. Now, lastly, I'll discuss a positive sequence model. This is what would be used in a positive sequence simulator, which is an electromechanical simulator. It looks very different from the other two because it is very different. The frameworks are changed, but it still does model power sharing and voltage and frequency controls. And within these blocks, there are nested controls and transfer functions, but for simplicity and in conjunction with how the other models were shown, this is how I've represented it here. This model is very computationally efficient and is used in system level studies to simulate whole regions like states. However, as mentioned earlier about positive sequence modeling, this type of model can't capture harmonics, specifically high frequency harmonics, and the system has to be balanced. And this is commonly not found in distribution systems, meaning distribution systems are often unbalanced. And in distribution systems, there can be a lot of inverter-based resources, such as those being installed on rooftops. So now I want to zoom back out and talk about why do these different model types matter. We got pretty detailed there. So first, going back to events and stability, we need to define the problem space. Of the power system events reviewed earlier, what events are we looking to study? Are we looking at planning activities, interconnection studies, frequency dynamics, voltage dynamics, and in microgrids or in really small systems, these frequency and voltage stability and events, they're kind of intertwined. So then from there, once we've defined our problem space, what timescale do these problems occur in? And then from there, what type of simulators work at this timescale and can accurately capture these events? We've talked about how electromechanical solvers and positive sequence solvers, they're very computationally efficient. However, they don't capture some of the high frequency harmonics or unbalanced nature that can happen. And then within the simulator, which type of model should you use that has the right control functions included in it that will work for the stability issues that you're trying to address. These are important and sometimes hard questions to answer. And with the increased presence of inverter-based resources, the answer to these questions has and will likely to change. And oftentimes when you approach a problem, specifically problems that have a lot of power electronics, you have people coming in from a power electronics background and people coming in from a power systems background. And these folks tend to think about these problems differently. And so it's very important to make sure everyone is on the same page in terms of terminology, stability, and what you are looking to solve. So now I want to get folks really excited about power engineering. So what engineers work on the electrical grid and do this type of analysis and use the type of tools that I was discussing? Now I have a lot of different engineering jobs that are related to electric utility on this page, and not all of them, use the types of models or simulators that I was talking about. But there are so many different types of engineers that work at all the timescales and events. They go from protection and substation engineers all the way up to transmission planning engineers. And this is in no way an exhaustive list, but I wanted to share it here to give some kind of guidance on keywords when looking for jobs that interest you. In a whole nother realm of electrical utility, of an electrical utility, is markets, which are the folks that either run or design the markets that decide the rules for who's going to be, which generators are going to be compensated and how are they going to be compensated. There's capacity markets, which are long-term, and then there's day-ahead scheduling, or that 15-minute dispatch that I talked about earlier. And to hopefully further excite you about the electric utility industry, guess what? A lot of people are going to be retiring in the electric utility industry in the next couple of decades. So there's going to be lots of jobs, and it's a very exciting time to be in the field as well. I realized this presentation is actually like half the length that it was supposed to be, but I'm going to go to the final slide of the day. This is the control room at ISO New England. ISO is Independent System Operator, who is the transmission system balancing authority, market operator, and reliability coordinator for New England. The folks who work in this room are the ones that keep the system running day to day and get it back online, calling generators and getting them back online and coordinated events to prevent or preempt cascading outages. They also have really neat jobs. And so that actually concludes my presentation. Sorry, Mohammed, it was quite fast. Thank you very much. I hope there were some interesting takeaways, and I hope I've interested at least one person in becoming a power engineer. If anyone is interested in pursuing a graduate degree in electrical engineering and power systems at UAF, please reach out to me. Thank you and happy Friday, and I welcome all questions. I realize I ended quite early, so hopefully there's lots of questions.
Thank you very much, Dr. Cicilio, for the very informative presentation. And those of you who are online, if you have any questions, please type in the chat window. Well, while we are waiting to receive the first question, maybe I can ask a question. Dr. Cicilio, do you think increased presence of inverter-based resources could lead to a less reliable grid? Because our power grid is highly reliable now, right? So do you see, like, more planning required to accommodate, addition of renewable resources in future?
Yeah, that's a great question. And I know a lot of people have different strong opinions about this. So I've touched on this a bit in the presentation about, timescales of controls, and inverter-based resource controls are kind of like naturally through how they're physically performed are a lot faster than large synchronous generation. So and that's on a very short time scale. So very short time scale events, there's going to need to be protection, control setting changes, and then actual control settings of inverters. And then there's also kind of like observability and controllability issues involved with distributed energy resources, particularly when they come to be like a large portion of the generation profile, which is seen in California. And so when you don't have the resolution or the control settings aren't correct, these can cause reliability problems. But we're in a transition right now. And there is a lot of really smart people working on these problems and optimizing different controls and finding out, where do we need to put sensors in the distribution grid to be able to have the resolution of observability to be able to, predict potential challenges. So transitions are hard. And I don't think having more inverter-based generation of renewable energy in the long term, I think we'll have just as a reliable grid. But getting there, yeah, there's going to be some challenges. That's why I think this is an amazing time to be in the industry. There's challenges, lots of things are happening. And, individual people can make a big difference right now.
All right, we do have a question, and I think you just saw it. Any thoughts on the Texas power grid, and perhaps, as a follow-up to that, like, things that they might be able to implement on the cheap that would make it more reliable.
So I'm hesitant to say too much about the Texas power grid because, it's all really recent and we're going to learn a lot in, the next couple of days and weeks. And I'm sure there's going to be like investigations and lots of changes that are going to happen to make sure that this doesn't happen again, or at least not to the same severity. But I think I'll discuss a couple of the challenges that I've read about and am familiar with. So Texas is unique. So whether or not you know this, Texas has its own interconnection. So there's, the United States is separated into different interconnects, and Texas is its own, meaning that its own synchronous system is within Texas and like a part of Oklahoma. And there's only a few interconnecting tie lines to other regions. So in that sense, they have limited import power from other regions. So they kind of, to a certain extent, have to depend on their own generation profile. And they also have very unique market structures that really emphasize like the value of energy right now. They don't, unless there's been recent changes, they don't really have the structures to create a value or incentive for energy that is more long-term. That's just how some of the incentives work. So it's also different than the rest of the country in that way. And Texas has a lot of wind and a lot of natural gas. And so natural gas, when it gets cold, natural gas gets prioritized to our heat. So you can have shortages of natural gas for electric generators when you have a cold spell. So it's kind of like a perfect storm. And then also Texas doesn't usually have these really cold icing events. So there hasn't been any regulation to force wind generators to implement any icing prevention. So the wind generators were actually a very small portion of generation lots in Texas. Well, I shouldn't say very small, smaller than natural gas, but the wind generation did have the loss of wind generation did have a lot to do with the icing events. And then there was a lot of natural gas constrictions that impacted the ability of natural gas generators to produce electricity. And then in accumulation with all of this, some other generators just tripped offline. So I could kind of summarize these problems in one sense of, there's variability, or not variability, the value of having a diverse resource profile is pretty important. And the issues surrounding natural gas congestion and natural gas being used for heat over electricity is also, has also been identified as a large problem for the New England region. And then there's also, how do you value, where do you put the incentives in your markets? It's kind of hard to kind of justify putting a lot of money into something for an event that you don't know or can't guarantee is going to happen, because that means if nothing ever happens, you have an overbuilt system where people are paying more for electricity. So there's kind of this balance that needs to happen. And there's a lot of research in resilience versus reliability. And how do you value that? And then how do you put that in your market structures? So you have the generators or other, stability, other devices on the system, like storage out there that can help with these kind of like very rare events. There's a lot more here. Sorry, that was a bit of a long-winded answer.
Well, I think that was a very good answer. And yeah, it sounds like it's a pretty complex system. And like you said, trying to overcharge people may be what they're trying to avoid and not building it out a little more. All right. I do not see any other questions coming up. So that looks like all the questions we had.
Okay.
Let us just give it more, maybe 1 or 2 more minutes. And maybe I can ask one more question here, if that's okay. Yeah, this is more like a general question. So I see there will be more need for a dynamic modeling of power systems in future. So how could our students or our engineers get better prepared for future power system jobs, like more maybe control skills, or is there anything that you might want to recommend?
Sure, I can give my perspective on it. So first for, general power systems engineering, we need more power system engineering students to fill out the utility workforce. Power systems classes are not everywhere, not super common. And when there are close classes, there's not typically a bunch, but taking as many power systems classes as you can, I think is incredibly helpful because that's going to help you with power flow analysis. But then it's also really important to get into power system dynamics. And there aren't always necessarily classes on this, but it's very easily incorporated thing to undergrad research projects or graduate research projects. So becoming familiar with certain simulators like PSSE, some places use PowerWorld, a lot of PSLF. That's really important for like transmission systems, and some power systems classes incorporate that. And then for distribution systems, there's several different types of simulators, but getting your hands dirty with certain set of simulators, whether it be in class or through research projects, will be really beneficial. And then additional skills, which I think are going to become increasingly important in the future, is with like optimization methods. And these can be used for like using, collecting the phasor measurement unit data from the grid to kind of tune your models of your generators. And there's also lots of other applications of optimization, but that's one of them. And signals processing is also going to be very important. And I mean, this is just like from my perspective of what, what my research most closely relates with industry practices. But there's a lot of other good skills that would be beneficial.
Thank you. Okay, thank you very much, Dr. Cicilio, for the great presentation, and thanks all for joining us today. You all have a great rest of your day.